by 11:59 p.m. All you need to do once you're done with your video is upload it on YouTube, put the link in a PDF file, and just upload the PDF file. There are going to be two changes. Oh, sorry. I forgot. I keep on forgetting your name. Brandon. Yeah, so it's due 11:59 p.m. tonight. So like just before midnight tonight. There are two changes in homeworks. I have to ask your name. Would you mind using the handle link? Okay, I can try that. All right, okay. So the two changes that's going to happen and basically for homework 9 and 10 is one of the things that we didn't quite do, even though we were doing it in an ad hoc way, was for each question 2 and 3 there will be a sample input and output, or maybe more than one, just so that you have certain kind of input-output pairs to test an algorithm on to make sure that works. Of course, if you pass those test cases, that doesn't necessarily mean that your algorithm is absolutely correct, but if your algorithm is failing on those, then you definitely know something's wrong. Also, for these two homeworks, going forward, for questions that are where you have to design an algorithm, the proof idea to proof detail ratio would go up to 80:20 instead of 50:50. Among other things, that's how we do it in the exam, so I figured might as well just do it. So at the end of the semester, I'll ask for your feedback to see how these two changes went for you. If the feedback is positive, we'll make these changes permanent for next year. I did talk a bit on length about like midterms and final exams, and in particular, I talked to a few of you after the midterm temp grade, and I realized I was saying the same thing over and over again, which meant I probably should say this to everyone. So just go ahead and read up on the post. Kind of the quick takeaways are, I realized the midterm, as I said, I kind of always struggle between the trade-off of amount of time that's in the midterm and making a non-trivial midterm. And this year, probably the trade-off was worse than usual. But the good news is the finals, I mean, you shouldn't be under any time pressure. I think I've nailed down the trade-off for the final for the last many years. So you shouldn't have that much of time pressure for the finals. And the main thing is for the homeworks, make sure you spend time that's proportional to things that are relevant to your grade. Right? So I know question 1 can be fun, it can take a lot of time. Ultimately, it's just worth 11% of your grade. Right? So you shouldn't be spending a lot of time on question 1. Spend more on 2 and 3. And again, as proof details are worth like at most 20%, then focus more on algorithm idea, algorithm details, and proof idea. And if you still have time, then go ahead and spend time on proof details, but not otherwise. I still owe you guys kind of a response or comments on the feedback, so I'll start doing that over the rest of the week. I'll kind of maybe have multiple posts talking about various issues that were brought up. Are there any questions on logistics?
Right.
Oh, sorry, Tyler. Yeah.
So the 80-20 split, is it 80% proof idea and 20% proof details?
Yes. Yeah, not the other way around. Yeah, no. I mean, there is probably a place for the other way, but I don't think it's in this course. Any other questions? All right, so let's go back to the problem we were considering. So as a reminder, we're looking at the problem of you're given n two-dimensional points, and you want to output the 2 points that are closest. And the notion of definition is the Euclidean distance is the square root of sum of the squares of x differences plus y differences. And so in this example, the pair of green points are the closest pair of points. And we started with looking at a divide and conquer algorithm to solve this. And so what we do, so we make one assumption that all the x coordinates and y coordinates are distinct. It's not necessary. In fact, the algorithm that we could consider, you can modify to make it work for the more general case where the x coordinate and y coordinates need not be distinct. But let's make that assumption for simplicity. And then you sort all the points by the x values and pick the first n over 2. And the first n over 2 form the points in Q. The last n over 2 form the points in R. And the idea is then you recursively, since it's a divide and conquer algorithm, in Q and R, you recursively find the closest pair of points. So let's say the closest pair of points in Q are the 2 green points, and in R are the 2 blue points. Then a crucial parameter that we'll make use of is what I call delta, and this is the smaller of the 2 smallest distance just on the left part end, right? And we saw last time that, so initially you can sort P to get P of x, which is sorted by x value. You can similarly get P of y, which is P sorted by y value. So you can get that in n log n time. Once you get that recursively, you can compute Q of x, Q of y, R of x, R of y in linear time. And that's kind of crucial to the ultimate n log n time runtime that we want. And so if after recursion it turns out that the points in Q and R are well separated, that is, the distance between any crossing pair of points is strictly more than delta, you're done, right? Because then the closest pair of points is the smaller of the blue or the blue or the green pair of points. That's fine, and you would be done. But in general, that is not going to be the case. So we have to handle the more general case, and this is where we'll crucially make use of this parameter delta that we talked about. So the simple observation we're going to use is that the Euclidean distance between 2 points is greater than or equal to the difference of the x values. It's also greater than or equal to the difference in the y values, but we are not going to use that fact in the algorithm. And so in this case, so again, this middle line is the point that divides everything into half. And what we do is look at all sets of, so if the middle value, x value is x star, then you look at all points which have x values within x star plus minus delta, right? So you basically have these 2 parallel lines at x plus delta, and or x star plus delta and x star minus delta. And the point is, if you have, essentially you go through a bunch of cases, but the point is, if there is a crossing pair of points such that its distance is strictly smaller than delta, then both of them have to be within x star plus minus delta. Right? So here's one example where both points are outside kind of this box, then the difference in the x coordinates is 2 delta, and so in particular the Euclidean distance is at least 2 delta. But even if one of the guys was inside and the other guy was outside, you get the x distance value of strictly at least delta over here. And so again, the Euclidean distance is at least delta. And similarly, you look at the other symmetric case, it's also strictly more than delta. So what that means is, once we know the value of delta, and if there indeed does exist a pair of points that has distance strictly smaller than delta, it has to, both of them have to fall in this green box. So all we have to do is figure out an algorithm to compute the closest pair of points within this set, with the caveat that we don't care if the closest pair of points is more than delta, right? So if there exists a pair of points within this box with distance strictly less than delta, we want to find it, and not only that, we want to find it in linear time. So that's kind of the challenge. So given all of this, and assuming that there does exist this problem to solve this green box issue, so let's assume there's a closest in box that figure out the closest pair of points within S, which again is this green box that we saw in linear time. And then we went over this last time, but basically the idea is you divide everything up, sort P into Px and Py, divide into Q and R, and then recursively compute the closest pair of points in Q and R. And so if we look at all, the sorting is n log n, but after that every line that is not a recursive call is linear. And again, we are assuming we have closest in box in linear time. And so the overall runtime, if the runtime of this green box is T of n, then it's n log n plus T of n. And T of n satisfies the recursion that, let's say if T is smaller than 4 or any constant really, it's constant. Otherwise, you have 2 recursive calls, and then you're spending an extra linear amount of time. So this is pretty much exactly the same recurrence relation that we saw for Mozart, and we know that this recurrence gives you n log n. Okay? So assuming you can solve the closest inbox problem in linear time, the entire thing is n log n. So are there any questions on the algorithm other than, of course, how we can do this closest inbox in linear time? Okay, everyone good? Okay, so what we'll do for the rest of today is just implement this closest inbox thing in linear time. Now, unfortunately, I don't think I can write by holding this thing in my hand, so I'll have to move to the wireless mic. I'll try to not to move a lot, so hopefully that will be clearer. All right. All right, so it turns out that to implement the closest inbox problem, it just follows from a very nice lemma, which I call the Kickass property lemma. This is not the official name of the lemma, I just made it up. But it is really nice, so hence the name. So I'll just go ahead and state the lemma for you. So just as a reminder where we are, so if x star is my middle point, the left part is q, the right part is r, and I'm looking at points which are x within x star plus delta and x star minus delta, and so this shaded region is what we are interested in. And so I'm calling the shaded region S. And what I'm really interested in is does there exist two pair of points, one on the left half of S, the other in the right half of S, such that so this is a crossing pair whose distance is strictly smaller than delta. Right? So it turns out so I'm just stating the lemma right now. So for every pair of points P and P prime, such that they're both in S, such that the distance between P and P prime is strictly smaller than delta. Again, if there was a pair of points, crossing pair of points with distance strictly more than delta or greater than or equal to delta, we don't care, because it cannot be the closest pair of points. And if we look at the set of points in S, but sorted by Y, okay, so this is the pair of points that is in this box, but they are sorted by their y values. And if we look at the position of P and the position of P prime, let's say this is I and J. So such that Sy of I is P and Sy of J is P prime. So I'm just saying, let's look at where P and P prime fall in this sorted, the set of points S sorted by the y coordinate. If this is the case, and let's just assume J is strictly bigger than I. If J is smaller, we just switch P and P prime, so this is without loss of generality. So the really cool result is it says if you look at the difference between I and J, this is less than or equal to 15. Okay. Now, the cool part about this is not the number 15 per se, but the fact that this is a constant. Okay. And so just a couple of notes. So this number 15 is not the smallest you can make it. Okay, so you can make 15 to be 9, and this is not that hard to show. In fact, you can, I think, even make it as small as 7, I believe, is the smallest you can get over here. So I won't go into this. This is an exercise. So can be as small as 7. Okay. And again, as I said, the fact that it's 7, 9, 15 really doesn't matter. The fact that it's constant is kind of what's kind of amazing about this. And the second point is, like we had seen, that once you have P of y, you can get Q of y and R of y by just going through P of y and checking whether the point should be in Q and R. You can also compute the S sorted in y order from P of y in constant time. Okay. Are there any questions? All right, so then I have a question for you. So the question is, how does the Kickass property lemma imply the algorithm that we want? Imply the order n implementation of closest in box. So talk to your friends for half a minute. Let me know if you have any questions. If not, so I've not told you why the lemma is true, and that's what we're going to spend most of the time on. But what I want you guys to think about is, assuming this lemma is true, how can you use this to come up with a linear time algorithm for closest in box, which again, remember, finds the closest pair of points in S, assuming that it's strictly smaller than delta. All right, I think Mehmet had a question first. Sorry? How do we come up with the number 15? We'll see it in the proof. Brandon. Okay, yeah, so we'll see why the number. So I said, at this point of time, why 15 and why not something else, we'll see in the proof. And it comes out very naturally when we do the proof. But any other questions? How many of you think this lemma is cool? Thank you. All right. Okay, so assuming the lemma is true, how can you implement the closest in box in linear time? Matt?
Scan through as y, compute the distance between consecutive ones, then move out to 2, and once it's less than delta, then you found them.
Right, so the idea is, if there is a pair of closest points that has distance strictly smaller than delta by this lemma, their positions I and j is going to be less than or equal to 15. So what you do is, you have a counter that scans through each value of I, And for each fixed value of I, look at all the pair of points that are within the next 15 positions. Compute the minimum among them. Right, so you get for each I, you have the closest pair of points between I plus 1, I plus 2, I plus 3, all the way up to I plus 15. And then you get one pair for each I. And then you scan through all values of I, and then the closest among all of those values will give you the final one. Right? So let me, I guess probably a bit of a mouthful, so let me just write down. So here's how you would implement closest in box. So here I'm assuming, sorry, I think I'm changing the parameters from what was there on the slide. So here you assume as input you get S of y and delta as input. And so let's say your S of y had indices from 1 to n prime, and n prime can be as large as n, but obviously no bigger than n. So what you do is, so you scan through each one of them, and for each I, let pi comma p prime I be the closest pair of points among, so you look at the points which is the point at the ith position and point at the I plus 1th position, again the point at the ith position, point at I plus 2nd position, and so you basically look at all possible 15 guys, and then just because you have to end at some point, you have to take care of the boundary condition, so you take the min of this and n prime. Okay, so essentially you look at for each I the next 15 guys, or if there is no more next 15, then you just go till you hit the end. Right? So you have a bunch of these, at most 15 pairs of points. For each pair of points, you compute the distance, pick the minimum. That will give you p I and p prime I. And then let p comma p prime be the closest pair of points among pi comma p prime I for I from 1 to n prime minus 1. Okay. And then all you do is check whether this pair of points is strictly smaller than delta, and if so, you output. Okay. If distance between p and p prime is less than delta, then return otherwise maybe you just return null or something. So again, the closest in box has to return a pair of points is the closest in the crossing pairs, assuming it's strictly smaller than delta. If not, it can return null. Tyler.
Shouldn't it be sy minimum of I plus 14 because you're going up to 15 and I starts at 1? Because you're going from I equals 1.
Right.
So should it be I plus 14 because you're going up to 15?
No. So it's I compared with each of the next 15 guys.
Oh, okay.
So it's I plus 1, I plus 2, I plus 3. Actually, if you do 14, you'll still be right, because I said you can make 15 to be 9 or whatever. So the algorithm won't be wrong, but that's not what I meant. I want to talk to your friends for half a minute. Let me know if any questions. If not, we'll go ahead and then just prove the Kickass property lemma. All right, are there any questions? Mark.
Do you need to do anything differently to change between 15, 9, and 7?
So Mark's question is, do you have to do anything different 15, 9, and 7? The proof changes, yes. So the proof that we are going to do can only prove 15, though if you stare closely at the proof, it's fairly easy to go down to 10 or something pretty quickly. For 9 and 7, you have to do more work.
So if you're implementing it, you can just use 7?
If you're implementing this algorithm, you can just use 7, yep. Which asymptotically doesn't make any difference, but it's like a factor of 2, so why not? Mehmet.
This test of y is ordered by y coordinate.
Yes. So by definition, if I give you a set of points, say, I don't know, S, or P in general, then P subscript X is the point sorted by X, and P subscript Y is the same set of points sorted by Y.
Okay, and we're assuming that we can compute this in time.
Yes, it's not assuming it is true. So if you are not convinced, this is an exercise that if I give you P of Y, compute S of Y in linear time. Okay? Well, the idea is simple, right? How did he do Q of Y and R of Y? Right, we went through P of Y and checked whether the X value was less than or equal to X star or not. Here you just have to check whether it's between X star and plus minus delta. So it's very similar to how you would get Q of Y and R of Y from P of Y. And I'll make one final comment. In fact, it turns out that if you want to handle the more general case where X and Y values are not distinct, then all you need to do is kind of sort all the points by lexicographic order. So sort by X first, and for same values of X, sort by Y, and then still divide in the middle part as you're doing. And then you have to change this kind of scanning for QY, RY, and SY again similarly to make sure everything works. Okay. All right, any questions on the statement of the lemma, or why assuming the lemma is true proves this closest inbox in linear time? Oh, by the way, this is linear time because you have one loop and you're just spending constant amount of time in each loop. Amel.
You don't have this level where you do like overlay squared and just like iterate every pair.
I'm sorry?
I'm saying if we didn't know this lemma.
Yeah, I mean, if you didn't know this, the only thing we know at this point of time is just going through all of them. Yeah. All right. So we are not going to do the full proof, as has been the case for a while. So we'll do proof idea of Kickass property lemma. And the way I'm going to do this proof idea is very geometric, so I'm just going to draw pictures and prove by picture. Okay. So again, as a reminder, the situation is as follows. I have S of Y, I have P which is at position I, and P prime which is J. And I want to argue that the difference between I and J is at most 15. Okay. So for contradiction, let's assume that they're at least 16 apart. And the way we're going to come up with a contradiction is then show that these pair of points, we are also assuming that the distance between P and P prime is strictly less than delta. And so we're going to come up with a contradiction for that. So we'll show that if the difference is at least 16, then these 2 points are strictly more than delta apart. In fact, we'll show that they're strictly more than 3 delta over 2 apart. Okay. All right, so here's how we're going to do the proof. So I'm going to draw everything again. So we have our middle point X star. I draw the right half of S, which is X star plus delta. I have the left half, which is X star minus delta. Remember, everything to the left over here is Q, everything to the right over here is R. And what I'm going to do is divide up this space of S into delta by 2 by delta by 2 squares. So I'm going to draw a point. I'm going to draw these 2 lines which are delta over 2 apart. And then I'm going to just draw horizontal lines that are delta over 2 apart. So unfortunately, this is not to scale, so this is not coming out as squares as it should. But I guess in your mental model, you should think of each of these dotted rectangles as squares. Okay? So I just divided everything, all this space in S, into delta over 2 by delta over 2 squares. Okay? All right. Now, the first claim we're going to make is there will be at most one point in each of these squares. Okay? So the first claim, or in some sense claim, is every delta over 2 times delta over 2 square has at most one point in it. So we are going to do a proof idea of this part again by picture. So let's assume there are 2 points in this square. And the basic idea is, let me ask you this question to you. So if I give you a square, right, and I tell you you have to place 2 points that are both have to be within the square, but place them as far as possible, where would you place them? At the opposite corners, right? At the opposite side of a diagonal. Right? So I'm not going to prove this. I'm going to assume that this is true. But so let's say, assume P and Q are in the same square. So again, I have, so this is a delta over 2 by delta over 2 square. So I said as an exercise, the furthest pairs are at the diagonal corners. Now I'm just putting P here and Q here, but it could be over here too, doesn't matter. So either the diagonal or the, I guess the anti-diagonal works. Okay. But now if P is this corner and Q at this corner, the Euclidean distance between them is, by the Pythagoras theorem, is the length of this hypotenuse. Right? So this implies the distance between P and Q is less than or equal to square root of square of this distance, which is delta squared over 4. This is delta squared over 4. Square root of delta squared over 2, which is delta over square root 2. And then we're going to use the fact that square root of 2 is strictly more than 1. Right, so it's 1.4. This is strictly smaller than delta. But the important point to note is each of these squares are squarely inside either Q or R. None of these squares are straddling the middle point. So if I have 2 pairs of points within a square, both of which are within Q or both of which is R, and I have distance strictly smaller than delta, that contradicts my definition of delta, which was the closest pair of points in either Q or R. So, but square completely inside Q or R, so that implies contradicts definition of delta. Okay. And so that proves the claim that if you look at any of these delta over 2 by delta over 2 squares, you'll have at most 1 point. Are there any questions on this? If not, we are almost done. So if there are questions, I'd like to take them. Now would be a good time to ask. Amen. Right, so now we are saying we have 2 points P and Q which are within the square. which means both of these points are completely within Q or completely within R. And we have just argued that the distance is strictly smaller than delta. But delta by definition is the smaller of the closest pair of points distance either within Q or either within R. In particular, if you take 2 points which are within Q, both of within Q or both of within R, they have to have distance greater than or equal to delta. Okay? Any other questions? All right, so with this lemma in hand, let's try and prove what we want. And so I'm not going to prove the rest of the argument in general case, but again, as I said, do prove by picture. And it turns out for this argument, kind of the worst place to put I, the ith point, is over here, right? So this is where my P is. And what I'm going to do is, I'm just going to try to pack in all the next 15 points. So remember, we argued that P prime is I plus 16. So we somehow have to fit the next 15 points in these squares. And by the claim, I can fit only 1 point in each square, right? So it's just a matter of counting at this point of time. So when I say 1, what I really mean is I plus 1. So let's say I put 1 over here, 2 over here, 3, again this is I plus 2, I plus 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And now is where I can get to place my jth guy, P prime, right? And it turns out if we look at this picture, the closest you can get is to put the jth guy over here, right? But now note the difference between I and j. There are at least 3 squares stacked on each other. So this distance is 3 delta over 2. And again, now we use the fact that Euclidean distance 2 points is at least the difference in the y values. So this implies distance between P and P prime is strictly more than 3 delta over 2, which is strictly bigger than delta. And if I'm calling this assumption star, this, or maybe I shouldn't use star. Let me call this 1, equation 1. So this contradicts. And that's it. And so the reason the 15 came is because of this counting argument that we wanted to. Okay. So talk to your friends for half a minute. Let me know if you have any questions. If not, we are done. So we've, okay, Mark.
Being greater than 2 delta over 2 be big enough?
Bigger than, yeah, so just being bigger than, strictly bigger than delta would be enough. So that's another thing, you immediately see that we are can make this argument tighter. I don't think that is enough to get 7, by the way, but you can knock down 15 to something like 12 using those kinds of observations. Are there any questions? All right, so just to kind of situate ourselves back where we were, this flow chart, define the problem, design the algorithm, do its analysis, and then use data structures. So as I mentioned, we're going to use 3 general techniques of designing algorithms. So we've seen greedy algorithms. How many of you know which row this is? All right, if you don't, you should see it's Full Metal Alchemist. We also saw divide and conquer as the second technique. The next thing we're going to look at, starting in detail from Wednesday, is dynamic programming. And it turns out it's kind of similar to divide and conquer, like same but different. They're same because they both use recursion to solve smaller subproblems. But they're different because in dynamic programming, you're smarter about how you solve subproblems. In particular, in typical dynamic programming, you have to solve the same subproblem multiple times. So you need to remember those so that you're not redoing them. Sorry for going over a bit. I'll talk to you guys Wednesday.